Hello, my name is Franz Giessibl and I'm gonna talk about our new paper, Evidence for Temporary and Local Transition of sp2 graphite type to sp3 diamond type bonding induced by the tip of an atomic force microscope. Now this work is really long, it has stretched over 8 years, it took us quite a while to get this published, and part of the reason is that we don't call it a proof for this, we call it evidence, but we think it's still important enough to be published and to be discussed in the community. So the diamond structure is of course well known, and what's probably not so well known is that graphite and diamond are relatively easy to transform into each other. So if we look at a perfect graphite, this is not perfect, I'll get to that later. So we have graphite, we have the sp2 bonded layer of graphene, and then we have a 3.3 angstrom distance between them, and they are van der Waals bound, and the stacking is AB. But so if we compress these layers, we can actually form a diamond bilayer, which is just like here. And now the question was, more than 8 years ago, we observed in our atomic force microscopy experiments, when we exerted pressure on the surface of graphite, that we got some high anharmonic components in the oscillation. And that even we already saw that in 2004 when we performed with a very blunt metal tip force microscopy at low temperature in vacuum on graphite. We also found higher harmonics, and these higher harmonics were consistent with the tip images we got from that were consistent with a height change of the A and B atoms. So in other words, the A atoms, which have an atom underneath, were lower and the B atoms stuck out, and those B atoms then created multiple images of our tip front atom. So now we get back to this problem with a very well-defined tip, with the famous carbon monoxide terminated tips, which had been introduced by Leo Gross and Gerhard Meuer and co-workers who imaged wonderful organic molecules with these tips. And now what happens if you use such a tip? It's relatively flexible. So if you approach with such a tip, it will always find the local minimum and then stay there. But then if you keep pressing downwards, we observed experimentally that there is all of a sudden a third harmonic created in the cantilever oscillation. And this third harmonic is created if the force profile of the tip versus sample interaction looks like this. You overcome a bump and then it goes down and then it goes up again. So this is the approaching distance. You're getting closer and closer here. So if your cantilever runs through such a force profile, you would generate a third harmonic A3 in the cantilever oscillation. And that is what our data showed here, and that's how we tried to understand this data. This is also, I mean, the first data on this was actually recorded more than 8 years ago by Thomas Hofmann, who was a PhD student at that time, also by Daniel Meuer, and later with Alex Liebig, who used other tips on that, and also J Weymouth. And we were supported by DFT, by Xinguo Ren, and also the STM data was explained with Andrea Donarini, who is a theoretical physicist here in Regensburg. So the story you can find in our paper. Please have a look and enjoy. Thank you.